Title of the module: Cayley's theorem and problems in group theory. We have already encountered the symmetric group Sim of G in the previous modules, which is a group of all permutations on a set S. It was one of the very first examples of a group. In fact, it is an important group partly because of the Cayley's theorem, which we discuss in this section. Cayley's theorem represents a group as a subgroup of a permutation group up to an isomorphism. This is often advantageous because permutation groups are fairly concrete objects. For example, it is straightforward to write programs to do arithmetic in finite permutation groups. We shall now see the Cayley's theorem. Any group G is isomorphic to a subgroup of a symmetric group of G, which is denoted by Sim of G. Let's see the proof. Let us take an element G belonging to G and we define a mapping lambda G, lambda suffix G here, but we'll call it as lambda G, from the group G to G by lambda G of x is equal to Gx. So, G times x for all x belongs to G. Now, this is a well-defined mapping because if we take x is equal to y, then Gx is equal to Gy, so that lambda G of x is equal to lambda G of y. So, we shall now show that lambda G is 1 to 1. Before that, we shall see that it is a homomorphism. Lambda G of x plus y is equal to G of x plus y. So, this is the mapping here, lambda G of x is equal to Gx. So, when there is x plus y, we have G of x plus y, which is G of x plus G of y, that is equal to lambda G of x plus lambda G of y, and therefore, we have now shown that the homomorphism property holds. The second one, we are going to show that it is 1, 1. So, lambda G of x is equal to lambda G of y implies that Gx is equal to Gy, and when you use the left cancellation property, you get x is equal to y. So, we started from this lambda G of x is equal to lambda G of y, and we have shown that x is equal to y. Hence, 1, 1 property holds. Next, we come to onto property. Take any y belonging to G. Now, this implies that there is a G inverse of y belonging to G, and this can be written as lambda G inverse of y, which is equal to y. Hence, we have shown that the onto property, for every element in the codomain, we have the corresponding pre-image in the domain, and therefore, lambda G belonging to Sim of G is also onto, and from this we have defined the isomorphic mapping from G onto G, and lambda G is this mapping. Let's go one step further and we define a new map called the wedge. The wedge is a map from G to the symmetric group of G. We define gamma from G to symmetric group of G by gamma of G is equal to lambda G being this mapping that we have originally defined. So, the homomorphism property is pretty much very straightforward. So, gamma of G1 plus G2 is equal to lambda G1 plus G2. So, this is the mapping. So, here lambda G1 plus G2, it's on the suffix, that is equal to lambda G1 plus lambda G2. This is equal to nothing but gamma of G1 plus gamma of G2. Therefore, homomorphism property is holding here. Next, 1, 1 property. Let us assume that gamma of G1 is equal to gamma of G2. This implies lambda G1 is equal to lambda G2. Now, from our earlier definition, it will become G1x is equal to G2x and all that. So, x will get cancelled and you have G1 is equal to G2, and therefore, 1, 1 property is also holding here. We can also say that the onto property holds because by virtue of the definition, gamma of G is equal to lambda G. So, whatever be the G element you take, whatever be the mapping, you can find a unique pre-image here in the domain. And therefore, onto property is very much obvious. And so, from here we have proved that this gamma or the wedge mapping is also a isomorphic property. From the properties of homomorphism, we know that if T is 1 to 1, then G is isomorphic to T of G. So, G is isomorphic to T of G implies that G is isomorphic to the wedge, or G is isomorphic to gamma of G. So, this mapping is isomorphic. If the group G is finite, then we can predict a group which is isomorphic to G. We shall now see a result. Every finite group of G of order n is isomorphic to a subgroup of Sn. Now, the proof is let G equal to A1, A2, so on up to AN. So this is any finite group of order n. So we have picked this particular group. We already know the wedge mapping that we saw in the previous theorem. Gamma of AI is equal to lambda Aj of AI. So that is equal to Aj AI. So this is the original thing that we learnt in the previous theorem. And now we represent it as a permutation. So A1, A2, so on up to AN can be mapped to AI A1, AI A2, so on up to AI AN. So instead of AI A1, we represent it as A theta I of 1, A theta I of n, so on. So, and when we replace AI by I, lambda AI becomes 1 goes to theta I of 1, 2 goes to theta I of 2, and so on up to n goes to theta I of n. So clearly you can see that this is in the form of a permutation, and therefore theta I belongs to Sn. So by the previous theorem we have said that theta 1, theta 2, so on up to theta n will be isomorphic to the wedge of G or capital gamma of G, and therefore this is isomorphic to G, and hence we have proved that every finite group of G of order n is isomorphic to a subgroup of a symmetric group n. Now we shall see an example to demonstrate the previous theorem. Example, consider the following Cayley table of a group G, E, A, B, C. So we are taking a 4-element group, so it has an identity element as well as 3 other elements A, B and C. You can see in the table that the Cayley table has been given here. So E goes to E, and all the mappings are being represented in the table down here. And now we are going to see the different cycles. Now we have lambda E. So this is the identity mapping. E A B C is going to E A B C, and correspondingly the theta 1, which is a permutation that will be mapped to it, is 1 2 3 4 1 2 3 4, and therefore this is represented by the cycle 1. Then lambda A is where E goes to A and A goes to E, B goes to C and C goes to B, so one jump. So theta 2 will also be 1 goes to 2, 2 goes to 1, 3 goes to 4 and 4 goes to 3. It can be represented as a product of those two cycles 1 2 and the cycle 3 4. Now lambda B will be E goes to B, A goes to C and B goes to E, and then finally C goes to A. And so theta 3 correspondingly will be 1 2 3 4, and 1 goes to 3, 2 goes to 4, 3 goes to 1 and 4 goes to 2. So it can be represented as the product of the two cycles 1 3 and 2 4. Now lambda C will be E A B C going to C B A and E. So theta 4 will be 1 2 3 4 going to 4 3 2 and 1, which is represented as the product of the two cycles 1 4 and 2 3. Hence G is isomorphic to the subgroup 1 1 2 3 4. So the product of these two cycles, then product of the cycles 1 3 and 2 4, product of the cycles 1 4 and 2 3, and so you can see that it is isomorphic to the subgroup 1 2 3 4, that is the cycle 1 2, product of cycle 1 2 and 3 4, and the product of the cycle 1 3 and 2 4 of S4. These are the, it is a subgroup of the symmetric group S4. So we have now demonstrated by means of an example the application of the previous theorem. We are at the fag end of the group theory modules that we have been studying for the last few weeks, and this is the last module of group theory. So let us solve some problems in group theory. Let's see the first problem. We have to prove or disprove that G is equal to 0 1 2. This is a group. We are going to see whether this is a group, and the operation star operation being defined as modulus of A minus B. So already we know that when we denote it by star G comma star, star can be any operation, and in this case we have defined it as modulus of A minus B. So we know that the elements are 0, 1 and 2. So let's draw the Cayley table for this particular group. It's not exactly a group, it's only a set now. So 0, 1, 2, 0, 1, 2. So 0 minus 0, 0. So we are applying this operation, therefore 0 minus 0, 0. 0 minus 1 is actually minus 1, but when applying the modulus it becomes 1, positive 1. And 0 minus 2 is minus 2, but applying the modulus operation it is 2. Similarly, we can do this for all the elements. So 1 minus 0, 1, 1 minus 1, 0, 1 minus 2 is 1, 2 minus 0 is 2, 2 minus 1, 1, 2 minus 2, 0. Now from the Cayley table we can see that the closure property holds. We can also see that 0 is the identity element of the group, and let's check for the inverse. We can see that 0 is here, which means that 1 is the inverse of itself. Similarly for 2, 0 is here, which means that 2 is the inverse of itself. But the only property that fails here is associative property. So let's check for that, because 1 star 2. Now this is equal to 1 star 1. So 1 star 2 means what will happen? So 1 minus 2, which is minus 1, but when applying modulus it becomes 1. Therefore 1 star 1 means so 1 minus 1, so 0 we get here. But when you are moving the brackets from here to here, so 1 star 1 star 2. So this becomes 0 star 2. So modulus of 0 minus 2 is 2. Both the values are completely different, and therefore we have shown that the associative property does not hold, and hence G comma star is not a group. In this problem we shall find the center of the group S3. We know that the center of a group has been defined by the set of all x belonging to G such that xy is equal to yx for all y belonging to G. Now for an abelian group, the center of the group is a group itself, because the commutative property holds for every element in an abelian group. But let's consider a non-abelian group here, and which is why we have taken a symmetric group, especially S3. And these are the permutations of S3. So you have I and the cycle 1, 2, cycle 1, 3, cycle 2, 3, cycle 1, 2, 3, cycle 1, 3, 2. So these are the elements of the symmetric group S3. Let's check which two elements commute with each other. For example, let us consider these two cycles 1, 2 and 1, 3. So when we check for the product here, cycle 1, 2 times cycle 1, 3, I have elaborated here in this operation here. So 1, 2, 3. So cycle 1, 2 has been represented as 1 goes to 2 and 2 goes to 1, 3 goes to 3 itself. So that's the meaning of this cycle 1, 2. And similarly cycle 1, 3 is being written here as 1, 2, 3. So 1 goes to 3 and 3 goes to 1, 2 goes to itself. Therefore, this is equal to, when we are doing the product, it becomes, so 1 goes to 2 and 2 goes to 2. So we can write it as 1 goes to 2 here. Then similarly 2 goes to 1 and 1 goes to 3, and therefore we can say that 2 goes to 3. And here 3 goes to 3, 3 goes to 1, and therefore we can say that 3 goes to 1. So it is represented as a cycle 1, 2 and 3. When we do reverse it, so when we are checking for commutativity, now I am doing the product as a reverse path. So 1, 2, 1, 3, here it becomes cycle 1, 3 times cycle 1, 2. So that also we have checked here, 1, 2, 3. So cycle 1, 3 means it becomes this, and cycle 1, 2 becomes this. Again when we do the product, so 1 goes to 3, 3 goes to 3. So that has been written here, so 1 goes to 3. Then 2 goes to 2 and 2 goes to 1. Therefore 2 goes to 1. So this has been written as a cycle here. 3 goes to 1 and 1 goes to 2. So that is obvious. So 3 goes to 2. So 1, 3, 2 is a cycle here, and we can see that they are very different. So definitely the product of these two cycles are not commutative, which means that these two elements will not come under the center of this group. Let's check for 2, 3, the product of these two elements, 2, 3, 1, 2, 3. Again this yields the cycle 1, 3. The product of 1, 3, 2 and the cycle 2, 3 will yield the product cycle 1, 2. Again very different. Hence this element, these two elements also will not come under the product, will not come under the center of this group. Similarly, when we check for 1, 2, 3 and 1, 3, 2 also, this can be done as an exercise. You can check and see that this is also not commutative. So from this particular exercise, we can conclude that the only element belonging to the center of S3 is the identity permutation. Now in this problem, we shall verify whether the converse of Lagrange's theorem is true. Now what is Lagrange's theorem? It says that if G is a finite group and H is a subgroup of G, then order of H divides order of G. So what is the converse? If G is a finite group and there exists an element, an integer k which divides order of G, does there exist a subgroup of G which has the same order as K. So let's, in general, this particular statement is not true. Let us verify this, and we shall show that the statement is not true with respect to the symmetric group. Let us consider A4. A4, we know that this is the subgroup of S4, which is the symmetric group, and A4 will consist only of even cycles, and S4 will contain both odd and even cycles. So which means that order of A4 is exactly half that of order of S4, and therefore 4 factorial by 2, and therefore there are 12. Now 6 divides 12. Suppose order of H is equal to 6. Now assume that 6 to be some value K. So 12 is the order of the group. We have a number 6 which divides 12, but we are going to check whether there is a subgroup of A4 which has the same order as 6. So let us assume it is so, and let us suppose that there is the subgroup H such that order of H is equal to 6. Now there is a specific formula to find the 3 cycles in S4. So number of distinct 3 cycles in S4 is 1 by 3 times 4 factorial by 4 minus 3 factorial, which is equal to 8. Let sigma does not belong to H. This implies that sigma square does not belong to H. So we know that the number of distinct 3 cycles in S4 is 1 by 3 times 4 factorial by 4 minus 3 factorial is equal to 8. But our assumption is that the order of H is equal to 6, and since the number of distinct 3 cycles is 8, there is at least one permutation, namely sigma, which does not belong to H. So let us pick that particular permutation, sigma does not belong to H, which implies sigma squared does not belong to H, which implies, why do we take this so is because sigma squared, the whole squared, is sigma power 4, and that sigma power 4 can be written as sigma cube times sigma, but sigma power 3 or sigma cube is equal to the identity, and therefore that implies that identity times sigma. So sigma belongs to H. So sigma squared will imply that sigma belongs to H, but this is a contradiction to our assumption that sigma does not belong to H. Therefore this is not possible. This statement sigma squared belongs to H is not possible, and therefore we can say that sigma squared does not belong to H. Now let K be a group generated by sigma. So obviously this is going to be I sigma sigma squared, because sigma cube is not here, because sigma cube will become I here, 3 cycles. Therefore I sigma sigma squared. Therefore this implies that order of K is equal to 3, and order of and H intersection K will be I. Why is this so? Because H won't have sigma, it won't have sigma squared, but in K we have I sigma and sigma squared. H will obviously have I. Therefore the only element common to both H and K will be I, and therefore H intersection K is equal to I. Now let us consider the order of HK. So order of HK will be order of H times order of K by order of H intersection K. This is equal to 6 into 3 by 1. So order of H intersection K, here it is only one element, so 1. Order of H is 6, order of K is 3, and therefore it is equal to 18. But this is a contradiction to our assumption, because our order of H is said to be 6, and HK is a subset of A4. So A4 is our original group, and A4 is the alternating group, and HK. If H and K are subgroups of A4, HK is also a subgroup of A4, and order of A4 is only 12. But we are instead getting order of HK as 18, which is impossible, because H and K are subgroups, and therefore order of HK should also be a number which is less than order of A4. Therefore this is a contradiction. Hence we say that there is no group H with order equal to 6, and the converse of Lagrange's theorem does not hold. The next problem, we shall show that the union of 2 subgroups may not be a subgroup. Let H2 be one of these groups. So let H2 equal to the set of all 2n such that n belongs to Z, and we take H3 to be 3n, the set of all 3n such that n belongs to Z. So we are taking 2 subgroups H2 and H3, and where Z comma plus is the group of all integers, and H2 and H3 will be the subgroups of Z. Now H2 union H3 is not a subgroup, because 2 comma minus 3 will belong to H2 union H3, but 2 plus of minus 3 is equal to minus 1 does not belong to H2 union H3, and therefore we can say that this is not a subgroup. We shall now show that Z2 cross Z2 is not isomorphic to Z4. If Z2 cross Z2 is a cyclic group, then it has a generator whose order should be the same as order of Z2 cross Z2, which is equal to 4. But no element of Z2 cross Z2 has order 4. Let us consider the element 1, 1. Now when we are doing it twice, so 1, 1 star 1, 1 twice 1, 1 is equal to 0, 0. That is, the order of 1, 1 is less or equal to 2. Hence, no element can be a generator of Z2 cross Z2, because if it is isomorphic to Z4, we are looking for an element such that the order of that particular element should be equal to 4. Since no such element can be found in Z2 cross Z2, this is not a generator of Z2 cross Z2. Therefore, Z2 cross Z2 is not isomorphic to Z4. In the next problem, we are going to verify whether Z cross Z is cyclic or not. Now we know that Z is cyclic and it is generated by the element 1. Now let us suppose that A, B be a generator of Z cross Z. Since 1, 1 belongs to Z cross Z, there exists an integer m such that 1, 1 can be written as m times A, B, where A, B is any general generator. So m times A, B should yield 1, 1. So this implies that MA is equal to 1 and MB is equal to 1. So MA, B belongs to Z. So MA and B are in Z. So we are getting the possibilities for A to be plus or minus 1, and for B also it is plus or minus 1. So in this case it is true. But let us now consider a different element, say 1, 2. This is also an element of Z cross Z, but we don't have any integer m which satisfies the equation 1, 2 equals m of A, B. In this problem, therefore we can say that Z cross Z is not cyclic. Z by 4Z to Z by 6Z. Now let F be a homomorphism from Z by 4Z to Z by 6Z. Because it is a homomorphism, f of 4Z plus n is equal to n times f of 4Z plus 1, where n belongs to Z. This is by virtue of the homomorphism property. Now order of f of 4Z plus n divides 4. So the only possibility here is 1 or 2. We have to find an element which divides 4, which can be 1, 2 or 4. But since our codomain is Z by 6Z, there is no element of order 4 there, and therefore it only has to be 1 or 2. Now if order of f of 4Z plus 1 is equal to 1, so we are taking two possibilities, 1 or 2. So the first possibility is 1, and here it is f of 4Z plus 1 is the 0 of Z by 6Z. Why so? Because since it is equal to 1, we have to pick the identity element of Z by 6Z. Only that element has order 1. Therefore, 0 of Z by 6Z is equal to 6Z plus 0, and clearly you can see that because it's an identity mapping, it is a homomorphism. There is no need to verify here. Now let's consider the second case. If order of f of 4Z plus 1 is equal to 2, f of 4Z plus 1 is equal to 6Z plus 3. So we have to pick an element of order 2. So this is the only element with order 2 here, and therefore 6Z plus 3 is taken. And now we don't know for sure whether this is a homomorphism, and therefore we are going to check whether it is well defined and whether it is a homomorphism. Let's check for the homomorphism property first. F of 4Z plus n plus 4Z plus m. So n and m are random integers. So f of 4Z plus n plus m. Now if f of 4Z plus n plus 4Z plus m is equal to f of 4Z plus n plus m, this mapping is from this to 6Z plus 3. Therefore it becomes 6Z plus 3 times n plus m. So 6Z plus 3n plus 6Z plus 3m. That is nothing but f of 4Z plus n plus f of 4Z plus m. So this is the mapping, and therefore we have looked at the previous part. And from this we have proved that f of a plus b is equal to f of a plus f of b. We have reduced it to that form. So this is a homomorphism. Now we have to check whether this mapping is actually well defined. Let 4Z plus n is equal to 4Z plus m. Now we need to prove that this function f of 4Z plus n is equal to f of 4Z plus m. Now If this is true, then this implies that n minus m belongs to 4z. In other words, 3 times n minus m belongs to 12z, but we know that 12z is a subset of 6z, which implies that 6z plus 3n is equal to 6z plus 3m. Now, this is a property of subgroups, and therefore, we have applied that, and from this we can say that f of 4z plus n is equal to f of 4z plus m. This is because if a minus b belongs to the subgroup, let's say h, then we say that a plus h is equal to b plus h. We have applied that property here, and we have arrived at this result, and from this we can clearly say that it is a well-defined homomorphism. And now we have found the number of homomorphisms from z by 4z to z by 6z. Now, from this study we have found that there are 2 homomorphisms from z by 4z to z by 6z, namely f of 4z plus 1 is equal to 6z plus 0 and f of 4z plus 1 is equal to 6z plus 3. So, these are the 2 homomorphisms that we have found, and they are the homomorphisms that satisfy this condition. They go from z by 4z to z by 6z. So, considering the time, we have tried to solve as many problems here. Interested students can look into the script of this module in order to solve more problems. In this module, we studied about Cayley's theorem, which is one of the most important theorems in group theory. We also did some problems to understand the many concepts of group theory better. The best way to learn mathematics is by doing. I hope that these modules were useful to grasp the concepts of group theory. We shall meet soon in a session of ring theory. Thank you.